Assalamu alaikum. This is the proof of Euclid's theorem or the division algorithm. Okay, now the proof statement is if a and b are integers such that b is greater than 0 and there exists the unique integers q and r such that a equals bq plus r where 0 is smaller or equals to r which is smaller than b. All right. So this is basically your actually this is the theorem that defines your basic mathematics. For example, if I was to say 15 divided by 2, I would say 2 sevens are 14, and this is what we come up with. We can also say that 2 multiplied by 7 plus 1 equals to 15. All right. So this can be our Q, this can be our B, this can be our R, and this can be our A. So this goes A equals BQ plus R, and R, this number, should always be smaller than this number. I mean, you cannot have a remainder bigger than this number right there. All right, you can never have a 3 here when a 2 exists over here. And secondly, this number can either be 0 or greater than 0. The remainder can never be a negative number. All right. So here's the analytic proof of this theorem. So let there be a set A of positive integers. All right. Let A be a set of positive integers, and we could say that A equals to A minus B of times X. I mean, A and B are integers, and we should also say that X also belongs in the groups of integers. All right, there are no fractions involved in this. Okay, there are only numbers 0, 1, 2, 3, 4, 5 up to so on. So capital A, the set of A equals A minus B times X. This is the set. Okay, now if this is the case here, then this set must have a least number. All right, least number. So we can say A equals A minus bx, and since this is a positive integer, this is a set of positive integers, this should always be greater or equals to 0 such that x belongs to the group of integers. All right, this is the set we have. Now if 0 belongs in the set of A, all right, then 0 should be the least number. If 0 belongs in A, then there is no positive integer below 0. All right. So 0 should be the least element of A. But if 0 is not involved in A, all right, so if A does not have 0, but it is a set of integers, all right, so it could be called a subset of positive integers, right? Because 0 isn't there. 0 is involved in the set of integers. So A is the subset of the set of integers. So we can write there, since as A being a subset of positive integers, sorry, A must have a definite least number. Okay, it must have a least number, something like so small that there is nothing smaller than that number. Let R be the least element of A. All right, the R is the number that there's nothing smaller than R. then we can say that since R also belongs in A, R equals to A minus B times X. Okay, now A minus BX is greater or equals to 0 as we have defined over here, and this is equals to R, therefore R is greater or equal to 0. So we have A minus BX equals R. Alright, this implies um, if we if we shift BX to the left side, we have A equals to BX plus R. Okay, and X is a variable, as you guys already know. X is a variable, and variable has many elements involved in it. So we can say that Q is another number that is involved in X. Let X equals to Q such that Q must be a group of must be involved in the group of integers. Therefore, we have A equals BQ plus R. Now we replaced X with Q such that R is greater or equals to 0. Now the theorem was, this part was the theorem right there. But there was also another thing. R should be a positive number, and R should also be lesser than B, which we have said over here. R should always be lesser than B, right? And we are now going to prove this part of the theorem. For this purpose, we try to prove the contrary, which is R is greater or equals to B. We have to prove that R is smaller than B. But for this purpose, to prove that, we are going to prove that R is not greater or equal to B. So if we try to prove the contrary of what we are going to prove, obviously our proof is going to have a contradiction. It will not have the proper result that we are trying to achieve, and hence the opposite of the supposition will be true. Therefore, if R is greater or equals to B, then this implies R minus B should be greater or equals to 0. R minus B should be greater or equals to 0. But R equals A minus BQ, as we proved earlier. So we're going to put this here. A minus BQ minus B should be greater or equals to 0. And if we take B common here, we have this. Now the Q was an integer. We suppose that Q was an integer, alright? Q was not anything other than an integer. So Q plus another integer should be an integer too, as Q belongs to a set of integers. Therefore, Q plus 1 also belongs in the set of integers. So we can write this as A minus BX is greater or equals to 0. Right? If this is true, then this number right here belongs in the set of A, because this was a criteria of a number belonging in A. And if this is true, this right here, then this should also be in A. And this was equals to this. we extracted this inequality from this one. So we can say r minus b equals a minus b times q plus 1 is greater or equals to 0. Therefore, r minus b belongs in the set of A. Okay, we proved that r minus b, whatever that number is, that belongs in the number A. Now r is some number, some least number of A, right? R should be the least number of A. But if there is another number that is subtracting from R, that is being subtracted from R, right? And it results in a positive integer. Now, R can never be a negative integer, right? I mean, the set of A cannot be negative. Set of A should be greater or equals to 0. That was our initial supposition. So R, a big number minus a small number, should result in something smaller than R. Should result in something smaller than R. But this right here is a contradiction, because that means that the number r minus b, whatever that number is, okay, let r minus b equals k, okay, let r minus b equals to k. This implies k is smaller than r, but r was the least number of a, and this was a contradiction. R cannot, and there cannot be any number that is smaller than r, but k, which is not equals to 0, is indeed smaller than r, which is against all of our suppositions. So we will write this is a contradiction to the fact that r is the least positive integer. Therefore, therefore, since all of this was proven wrong, therefore this contrary supposition is also proven wrong. If r is not greater or equals to b, then what can r be? It should always be smaller than b. Therefore, r is smaller than b. It's like saying that I have two men, okay, this and this, right? If I say that I have to prove that this guy is smaller than this guy, if this guy is smaller than this guy in height, then either I will just measure both the lengths and say that obviously this length is smaller than this length, so it proves. But if we do not have the tendency to measure the lengths, we have another way, that we suppose that maybe this guy is smaller than this guy, or this guy is equal to this guy, right? And of course, through our calculations, this result will be proven wrong. Hence, the opposite of our supposition will be proven true. Therefore, we will obviously assume that if the contrary of what we want to prove is wrong, then obviously the opposite should be true. And this is what we did here. This is usually called proof by contradiction. Now, we are going to prove the uniqueness of Q and R. We had, to prove uniqueness of Q and R. Now we have A equals B times Q plus R, where A, B, Q, and R, all of them are belong into the set of integers. So for all A, B, Q, R belong in the set of integers, and what we gathered from before, 0 is smaller or equals to R, which is smaller than B. All right. So this is what we have right now from what we get. Now to prove uniqueness, we will suppose that instead of Q and R. We have to, by the way, prove the uniqueness of Q and R, that there can be no other number than Q and R themselves. We are going to again prove by contradiction. We are going to suppose no, there can be another numbers, Q1 and R1. All right, they are different from Q and R. All right. So, and at the end, what are we going to have? Q should be equals to Q1 and R should be equals to R1. Or we can also suppose, let there be other integers, I can say s and t in place of Q and R. All right, in place of Q and R. Therefore, we will have A equals B times S plus T. All right, for all A, B, S, T belongs into the group of integers, and 0 is smaller and equals to T, which is smaller than B. Okay, we name this equation as 1 and we name this equation as 2. Now, since both the numbers are equal to same number, like BQ plus R is equals to a number, and that number is also equals to B, S, and T. So we can write, combining 1 and 2, we have BQ plus R equals to BS plus T. All right. Now, to prove this, I am going to involve some algebra. Shift BS to the left side and R to the right side. BQ plus BS should be equals to R plus T. Okay. Oh, sorry. The signs will change. Like this is a positive number over here, and this will come as a negative number here, and R is a positive number over here, and it will come as a negative number over here. I'm gonna write it a bit neatly over here. There. Now, let me name this equation as 3. Okay. Now, I can also say that BS minus BQ equals to R minus T. Like, basically, I pulled a minus sign from both sides. I mean, I multiplied both sides by -1. It's possible. 4. This also implies combining 3 and 4, we have plus minus BQ minus BS equals plus minus T minus R. And this implies BQ minus BS mod should be equals to T minus R mod. Okay, the difference of both the numbers, no matter what the arrangement is, should be equal. Now, as we know that T is smaller than B and R is also smaller than B. Let's suppose R, just to show you an example, R equals to 2, okay, and this T equals something 3, and B is something bigger than both the numbers, we can say 5. So the difference between these two numbers should always be smaller than 5. No matter what the numbers are, if both of the numbers are smaller than B right here, then the difference of these two numbers should also be smaller than B. So we can say that since T is smaller than B and R is also smaller than B, therefore the mod of T minus R should be smaller than B, mod of B, right? Therefore, using this information in 5, we have BQ minus BS should be equals to the mod of oh sorry, should be smaller than the mod of B. All right, this should be smaller than the mod of B. Okay, now if we take extract the mod of B out of this, we can say mod of B Q minus S is smaller than B, right? And if we divide this mod of B to the right hand side, we will have mod of Q minus X S should be smaller than 1. Now Q is an integer, a positive integer, and S is also a positive integer. Since Q, S belongs in A and A is the set of positive integers, therefore this will also result Q minus S should also belong in A. This will also result in a positive integer or maybe a negative integer. All right, but but since it's a mod, it will always result in a positive integer, since this is a mod here, and mod always gives a positive value, and an integer minus another integer should also give an integer. So Q minus S belongs in the set of A, and the only integer smaller than 1 is 0. Therefore, if this is smaller than 1, then I can say that mod of Q minus S should be equals to 0. And this implies Q is equals to S. I'll name this equation as A. Now, I have proven the uniqueness of Q. Like if I suppose any other number, S, T, M, N, any number, this will always result in the same number that Q is. Like both of them will be the same number. All right, this is the uniqueness of Q. Now I'm going to prove the uniqueness of R using A, that Q equals to S, in this equation, in equation 5. Actually I shouldn't, it's equation. So we have mod of B times Q minus B times S, but S equals to Q, so we can write this like this, equals to T minus R, mod of T minus R, and this will result in 0 equals to T minus R, and this will also imply T equals to R. So A and B prove the uniqueness of Q and R. Hence, we have proven that A equals B times Q plus R if all of these four numbers belongs to integers, and Q and R are unique integers. Like there can be no other numbers except for what Q and R are. Right? Thank you very much.